When we think about the history of astronomy, our minds often travel to the iconic discoveries that reshaped humanity's understanding of the cosmos. Galileo turning his telescope toward Jupiter and sketching its moons, Edwin Hubble revealing the existence of galaxies beyond our own, or Clyde. Tombaugh uncovering Pluto at the edge of our solar system. Yet there is a quieter, equally profound discovery that deserves to be told in the same breath. The moment Triton, Neptune's largest moon, entered human knowledge in 1846. It was not only a discovery of a celestial body, but also the unveiling of a mystery so profound that, even today, it challenges astronomers, physicists, and dreamers alike. Triton is not an ordinary moon. It does not follow the patterns of loyalty that moons typically exhibit to their planets. Instead, it rebels against convention, orbiting Neptune in a retrograde direction, moving opposite to the planet's spin, as if whispering to us that it does not belong, that it came from somewhere else, that it carries the story of another world, another time, perhaps even another destiny. To understand the magnitude of Triton's uniqueness, one must first imagine the backdrop of its discovery. The year was 1846, a time when the boundaries of the solar system were still being drawn. Neptune itself had just been discovered through a feat of human intellect and mathematical precision, its position predicted by Urbain Le Verrier and John Couch Adams before it was ever seen through a telescope. Within days of this milestone, the British astronomer William Lassell trained his telescope upon the newly found planet. His instrument was not grand by modern standards, yet his vision was unclouded by doubt. There, orbiting the faraway blue dot, he spotted a companion, what we now call Triton. Imagine the weight of that moment. Humanity had just extended its sight to the farthest reaches of the solar system then known, and in that distant darkness, not only had a new planet been revealed, but also a moon that would later prove to be unlike any other. It was as if the universe, in its poetic generosity, rewarded our curiosity with a gift wrapped in enigma. What sets Triton apart from the other moons of the solar system is not simply its size or its orbit, but its very defiance of expectation. Most moons form alongside their parent planets, emerging from the same swirling disks of dust and gas that give birth to the worlds they accompany. They move in harmony, orbiting in the same direction as their planet spins, bound by the logic of celestial mechanics. But Triton refuses to conform. Its retrograde orbit tells us that it was not born of Neptune's embrace. Instead, it was captured a wanderer, likely from the icy Kuiper belt beyond Neptune, pulled into Neptune's gravity through a cosmic encounter of staggering improbability. This capture is not merely a curiosity, it is a cosmic drama, one that speaks to the violent, dynamic past of our solar system. Picture an icy body once drifting free in the outskirts of the sun's domain, suddenly ensnared by the immense gravity of Neptune. To be captured rather than collide, its trajectory had to balance on the knife's edge of chance. In that delicate moment, the story of Triton was rewritten. It was no longer a solitary traveler, it had become the reluctant moon of a gas giant. Its fate was forever altered, and with it, Neptune gained a companion that defied the norms of planetary science. The consequences of this capture echo through every aspect of Triton's existence. Its orbit is not only retrograde but also tilted, inclined at a steep angle relative to Neptune's equator. This peculiarity suggests that Triton's arrival may have disrupted the balance of Neptune's original satellite system, scattering or even destroying the moons that may have once circled the planet. Triton is a usurper, a conqueror, and in its presence, Neptune's celestial court was forever rearranged. This uniqueness is not a matter of poetic imagination alone, it is written in the orbital mechanics, in the scars of gravitational upheaval, in the absence of the moons that might have been. In a way, Triton's story is not unlike our own. An outsider arriving in a new domain, reshaping its environment, carrying with it a past that can never be entirely hidden. What is even more remarkable is that Triton is one of the very few large moons in the solar system that exhibit such an orbit. Among the scores of moons orbiting the gas and ice giants, most follow predictable prograde paths, moving with the spin of their planets like dancers in synchronized motion. Triton alone breaks the rhythm, moving against the current. A reminder that the universe is not governed by uniformity, but by exceptions, by anomalies, by singularities that defy the neat patterns we expect. If Jupiter's moons tell us about the grandeur of planetary formation, if Saturn's rings reveal the delicacy of cosmic balance, then Triton tells us about disruption, about capture, about the unpredictable hand of chance that shapes the destiny of worlds. But Triton's uniqueness is not confined to its orbit. Its size alone demands attention. It is the seventh, largest moon in the solar system, larger than Pluto itself, which once held the status of a planet. This fact is no coincidence. Many scientists believe that Triton and Pluto are siblings of sorts, both born in the Kuiper belt, both icy bodies carrying the chemistry of the outer solar system. Yet while Pluto remains in its distant orbit, a lone king of its small domain, Triton was pulled into the gravity of Neptune, forever tethered to the giant that captured it. This comparison adds depth to Triton's identity. It is not merely a moon, it is a displaced dwarf planet, a captured cousin of Pluto, an emissary from a region of space we have only just begun to understand. To explore Triton is, in a sense, to explore the Kuiper belt itself, to touch a fragment of the solar system's distant frontier without needing to travel all the way to its edge. The story of Triton's uniqueness deepens further when we consider the physical characteristics revealed to us. Unlike most captured bodies, which tend to be irregular, scarred, and inactive, Triton is a world of surprising smoothness and complexity. Its surface is a mosaic of frozen nitrogen, methane, and water ice, sculpted not only by ancient impacts but also by geological processes that continue to this day. Voyager 2's images showed us a world that is not passive, not dead, but alive with movement, reshaping itself in ways that moons are not supposed to. Cryovolcanism, geysers, and resurfacing hint at an internal dynamism driven by forces we are only beginning to comprehend. How can such an active world exist so far from the sun, in a place where energy is scarce and warmth is a rarity? The answer lies in part in Triton's capture itself. When it was pulled into Neptune's orbit, gravitational forces likely generated immense tidal heating within its interior, melting ice, creating subsurface oceans, and fueling geological activity. Even now, billions of years later, the echoes of that capture reverberate beneath its frozen crust. Triton's very uniqueness is preserved in the restless energy that animates its landscapes. This raises profound questions that extend far beyond the realm of Neptune's orbit. If Triton can sustain such complexity, if it can hold subsurface oceans in the cold reaches of the solar system, what does that say about the potential for life in unexpected places? What does that say about the resilience of planetary bodies to remain active against all odds? Triton, in its defiance of expectations, becomes not only a curiosity but also a beacon of possibility. It reminds us that the search for life is not limited to the habitable zone near the sun, that the spark of potential can exist even in the most unlikely environments. Its uniqueness is therefore not just scientific but philosophical. It challenges our assumptions about where life can exist and what conditions are necessary for it to flourish. And so, the discovery of Triton in 1046 was not just the cataloging of another moon, it was the beginning of a conversation that continues to this day. Every telescope that turns toward Neptune, every mission concept designed to return to its orbit, carries within it the weight of Triton's mystery. We long to return, to peel back the layers of its frozen crust, to dive into its hidden oceans, to listen to the echoes of its captured past. For Triton is not a moon that can be easily dismissed or explained. It is an outlier, a rebel, a messenger from the edges of the solar system. Its uniqueness lies not only in its orbit, not only in its geology, but in the way it forces us to confront the unpredictability of the universe itself. When we gaze at Triton, we are reminded of the fragility of certainty. We are reminded that not everything in the cosmos follows neat rules, that chaos and chance are as much a part of creation as order and symmetry. Triton teaches us humility. It shows us that even in the vastness of space, where distances stretch beyond comprehension, there are worlds whose stories are deeply personal, filled with drama, conflict, and transformation. To explore Triton is to explore a narrative of capture, survival, and adaptation, one that resonates with our own human story. We too are wanderers, captured by curiosity, driven by forces we do not fully understand, reshaped by encounters that alter our destiny. Triton is a reflection of us, frozen in ice, moving against the tide, carrying with it a reminder that belonging does not always come from birth, but sometimes from the chance embrace of a larger force. Thus, when we speak of Triton's discovery and uniqueness, we are not merely recounting an astronomical fact. We are telling the story of a world that embodies the unpredictable artistry of the cosmos. It is a story that began with a telescope in 1846, that expanded with Voyager 2 in 1989, and that continues today as we dream of missions yet to come. Triton is not simply Neptune's moon, it is a cosmic paradox, a captured planet masquerading as a satellite, a rebel bound to a giant, a symbol of the universe's refusal to be ordinary. And in its uniqueness, it invites us to dream bigger, to look farther, and to never stop questioning the mysteries that lie beyond. When Voyager 2 approached Neptune in 1989, humanity experienced a moment that felt like standing at the edge of a vast ocean, staring into waters we had never sailed before. The spacecraft had already gifted us unforgettable views of Jupiter, Saturn, and Uranus, each encounter stretching the imagination and redefining what we thought we knew about our solar system. Yet when it came to Neptune and its moon Triton, the stakes felt different. This was the last of the giant planets, the most distant of them all, and Voyager 2 would be the only emissary of Earth to ever make that journey in our lifetime. What it uncovered at Neptune's moon Triton remains one of the most breathtaking chapters in the history of planetary exploration, because for the first time we realized that even in the coldest, darkest reaches of the solar system, a moon could be alive with activity, restless and dynamic. The approach to Neptune was filled with anticipation. For centuries, Neptune had been a world glimpsed only through faint telescopic images, its features hidden, its moons barely distinguishable. Even with Voyager 2 closing in, astronomers expected Triton to be little more than a frozen rock, a relic of a distant frontier. After all, the sun's warmth was nearly 100 times weaker there than on Earth, and surely, most assumed, nothing could stir beneath such eternal cold. But as Voyager drew closer, what it revealed shocked the world. Triton was not dead. Its surface was alive with processes no one had dared to predict, reshaping not only the moon itself, but also our understanding of where activity could exist in the cosmos. The first images that trickled back showed a landscape unlike any we had ever seen. Instead of a battered, crater-ridden wasteland like our own moon, Triton displayed smooth plains, ridges, and peculiar terrains carved into strange, cantaloupe-like patterns. This meant something extraordinary. Its surface was being renewed, resurfaced by active processes that erased the scars of impacts over time. On a moon that far from the sun, such activity was not just unexpected, it was revolutionary. Here was proof that even in the outermost corners of the solar system, geological forces could still be at work. Triton was no relic, it was a world in motion, and then came the revelation that stunned scientists most of all. Voyager 2 detected active geysers erupting on Triton's surface. Imagine the sight, dark plumes of gas and dust blasting upward, stretching as high as 8 kilometers into the thin atmosphere, casting shadows that extended for hundreds of kilometers across the icy plains. These geysers were not powered by liquid water like those on Earth, but by frozen nitrogen that, warmed ever so slightly beneath the surface, expanded and burst through the icy crust. This was the first time active eruptions had ever been seen on a moon so far from the sun. The idea that sunlight, faint though it was, could trigger such eruptions showed the extraordinary sensitivity of Triton's environment. The energy required was minimal, yet it was enough to keep the surface alive with motion. For scientists, this was a revelation not just about Triton, but about the principles of planetary science itself. It demonstrated that energy sources beyond the sun's direct warmth, such as tidal forces from Neptune's gravity and residual heat within Triton's interior, could combine with even the faintest sunlight to drive extraordinary activity. It suggested that moons and planets at the edges of our solar system might harbor complexities we had never imagined. Suddenly, the notion of icy worlds as lifeless and inert was shattered forever. Voyager also revealed details of Triton's thin atmosphere, composed primarily of nitrogen with traces of methane. This atmosphere, though tenuous, interacted dynamically with the surface, contributing to seasonal changes and the geysers themselves. To witness a moon so far from the sun with weather-like processes was nothing short of astonishing. It expanded our definition of what it meant for a world to be active. Until then, atmospheres and weather seemed the domain of planets like Earth, Venus, and Titan. But here was Triton, an icy body in the deep freeze of space, still breathing in its own way. Equally intriguing were the clues about Triton's geological history. Voyager's images revealed vast icy plains that appeared to have been resurfaced relatively recently in geological terms, alongside features that hinted at cryovolcanism volcanoes not of fire but of ice, spewing ammonia, water, or methane rather than molten rock. The implications were profound. Cryovolcanism suggested that beneath Triton's frozen crust there might exist reservoirs of liquid, possibly even an internal ocean. At Neptune's distance, the sun's heat is far too weak to sustain such conditions. The energy must have come from within, likely from the tidal heating generated during and after Triton's capture by Neptune. That capture, billions of years ago, would have stretched and squeezed the moon's interior, creating enough heat to melt ice and fuel the activity Voyager revealed. Even if much of that heat has since dissipated, the echoes of it still resonate in the processes we observe today. The uniqueness of these findings cannot be overstated. Before Voyager, many assumed the outer solar system was static, frozen in silence. With the exception of Jupiter's volcanic moon Io, moons were considered geologically dead worlds, preserved fossils of the early solar system. Voyager 2's encounter with Triton rewrote that script entirely. It told us that the solar system is not a quiet museum of celestial relics, but a dynamic, evolving collection of worlds, each with its own story, each with its own surprises. Triton, with its geysers and cryovolcanos, became the poster child for this revelation. The data collected in those fleeting hours during Voyager's flyby became a treasure trove for decades of research. Every image, every measurement sparked new questions. How long has Triton been geologically active? How thick is its icy crust? Does a liquid ocean still persist beneath its surface? Could that ocean, shielded from the freezing vacuum of space, harbor conditions suitable for life? Each question carried weight not only for Triton, but for countless other icy bodies scattered across the solar system. If Triton, captured and battered by its violent history, could remain alive, then what about Pluto? What about the moons of Uranus? What about the dwarf planets orbiting in the Kuiper belt? Voyager 2's discoveries ignited a revolution in the way scientists viewed these icy frontiers. There is also a human dimension to this story that cannot be ignored. Voyager 2's encounter with Neptune and Triton was not just another scientific mission. It was the culmination of decades of ambition, engineering brilliance, and courage. The spacecraft had traveled for more than a decade, billions of kilometers through the void, to arrive at a world we had only glimpsed as a tiny point of light. It had survived cosmic radiation, navigated the gravitational pull of giant planets, and continued to function far beyond its expected lifespan. To arrive at Neptune, take breathtaking images of Triton, and beam them back across the darkness to Earth was nothing short of miraculous. The pictures, grainy by today's standards but miraculous at the time, captured imaginations everywhere. They were splashed across newspapers, studied in universities, and marveled at in homes. They reminded humanity that even in the most distant corners of our solar system, wonders awaited discovery if only we dared to look. Voyager 2's revelations about Triton also set the stage for dreams of future missions. Scientists began to imagine what it would mean to send an orbiter to Neptune, to study Triton over years rather than hours, to land on its surface and peer beneath its icy crust. These dreams persist to this day, fueled by the tantalizing data that Voyager provided. Proposals for missions like Triton, a spacecraft designed to fly past Triton in the coming decades, owe their inspiration directly to that fleeting encounter in 1989. The hunger to return to Triton is not just scientific curiosity, it is a recognition that this moon may hold answers about the origins of the solar system, the processes that shape icy worlds, and perhaps even the possibilities for life beyond Earth. One cannot help but feel awe when reflecting on what Voyager 2 accomplished at Triton. In a matter of hours, the spacecraft transformed a distant, mysterious dot into one of the most fascinating bodies in the solar system. It took us from ignorance to wonder, from assumption to revelation. It showed us geysers in the darkness, nitrogen frost stretching across plains, and a moon that defied everything we thought we knew about how the universe works. It reminded us of the unpredictability of discovery, the way nature delights in shattering our expectations and humbling us with truths far stranger than anything we imagined. Even today, the images from Voyager 2 carry an almost mythic quality. They are a reminder that exploration is not just about finding what we expect, but about being surprised, about having our assumptions overturned, about realizing that the universe is richer, stranger, and more beautiful than we dared to believe. Triton embodies that lesson. It is not simply a moon of Neptune, it is a monument to the wonder of exploration itself. Voyager's revelations did not close the chapter on Triton, they opened it. They ensured that as long as humanity dreams of the stars, Triton will remain one of the great mysteries calling us to return. So when we speak of Voyager 2's revelations at Neptune's moon, we are speaking of more than scientific data. We are speaking of the moment we learned that even in the coldest shadows of the solar system, a moon could breathe geysers into space, could reshape its surface with icy volcanism, could challenge the very definition of what it means for a world to be alive. We are speaking of a moment when a machine built by human hands traveled farther than anyone had ever gone, and in that distant place, it revealed to us not just the secrets of a moon, but the boundless potential of human curiosity. Voyager 2 showed us that the solar system is not a set of distant, silent spheres, but a living, breathing family of worlds, and Triton, with its restless geysers and frozen beauty, remains one of the most extraordinary members of that family. Beneath the frozen surface of Neptune's largest moon, Triton, lies one of the most tantalizing mysteries in all of planetary science, the possibility of a vast subsurface ocean, hidden away in darkness, sealed beneath a crust of ice, and perhaps harboring secrets that could redefine humanity. Understanding of life in the universe. When Voyager 2 swept past Triton in 1989, the fleeting glimpses it captured of the moon's surface told us more than we had ever known. Yet they also left behind a trail of questions. Why was this distant world still active, erupting geysers of nitrogen and reshaping its terrain when the sun's warmth at Neptune's orbit is so faint that it barely registers as more than a glimmer? The answer, many scientists suspect, lies beneath the surface, in the concealed, shadowy depths of an ocean that continues to churn with the echoes of ancient energy. To even consider that an ocean might exist so far from the sun is to challenge the very assumptions that once guided astronomy. For centuries, humanity believed that life, and even liquid water, could only exist in a narrow band of space known as the habitable zone, the region around a star where warmth could keep water from freezing solid. Yet Triton, like Europa around Jupiter or Enceladus around Saturn, has forced us to expand that view. These moons remind us that there are other sources of heat besides sunlight, tidal forces, radioactive decay, residual heat from formation, and that these sources can sustain liquid water in places where we once believed only frozen silence reigned. Triton's retrograde orbit, its telltale sign of capture from the Kuiper belt, plays a key role in this story. When Neptune's gravity ensnared Triton billions of years ago, the forces unleashed were catastrophic. The moon's orbit would have been highly eccentric at first, stretching and squeezing the entire body with immense tidal stresses. This process, known as tidal heating, likely melted vast portions of its interior, creating subsurface reservoirs of liquid. Over time, as Triton's orbit circularized, the heating diminished, but evidence suggests enough warmth remains trapped inside to keep water in a liquid state beneath its icy crust. The clues left on Triton's surface strongly hint at such an ocean. Voyager 2 revealed a landscape scarred by cryovolcanism. features that resemble volcanoes but that would spew water, ammonia, and methane instead of molten rock. These icy eruptions imply a source of liquid or slushy material beneath the crust, ready to be expelled when pressure builds. The geysers Voyager observed, towering columns of nitrogen gas and icy particles, further strengthen the case. They demonstrate that there is energy beneath Triton's surface, energy strong enough to crack through ice and propel material into space. Where there is energy in water, even in frozen darkness, the door to habitability creaks open. The possibility of a subsurface ocean beneath Triton connects this distant moon to a broader family of ocean worlds across our solar system. Europa hides an ocean beneath its fractured ice, warmed by Jupiter's tidal grip. Enceladus boasts geysers that erupt with salty water from a global sea beneath its south pole. Even tiny Pluto, Triton's cousin from the Kuiper belt, shows signs that it may once have held or may still hold liquid beneath its frozen heart. What makes Triton unique is that it is both a captured world and one of the coldest large bodies in the solar system, yet it still shows signs of geologic activity. If it indeed harbors an ocean, then liquid water may be far more common across the cosmos than we ever dared believe. To imagine this hidden ocean is to picture a world utterly alien and yet strangely familiar. Imagine descending through kilometers of nitrogen and water ice, where temperatures hover near absolute zero, and then breaking through into a vast, pitch-black sea. The water here would never feel the kiss of sunlight, yet it might still be stirred by currents driven by tidal forces or by chemical reactions between liquid water and the rocky core below. In that dark ocean, chemistry could thrive. On Earth, life has proven it does not need sunlight to exist. It can flourish around thermal vents at the bottom of our oceans, where heat and minerals fuel entire ecosystems of creatures that live in perpetual darkness. Could Triton's ocean, shielded from radiation, rich in chemicals delivered by comets or preserved from its Kuiper belt past, provide a similar cradle? The idea is no longer pure speculation. It is supported by the growing recognition that life may not be rare in the universe, but rather resilient, capable of emerging wherever water and energy combine. The implications of such a discovery are staggering. If Triton holds a subsurface ocean, and if that ocean harbors even the simplest microbial life, then the entire framework of our search for life beyond Earth must expand. No longer would we look only to Earth, like planets orbiting stars within their habitable zones. Instead, we would realize that life could thrive in icy moons, in hidden oceans, in places that seem inhospitable from the surface but teem with potential below. Triton could teach us that habitability is not an exception but a rule, that the universe may be far more alive than we ever imagined. But even if no life exists in Triton's ocean, its presence alone would be a treasure of knowledge. Studying such an ocean would reveal secrets about the moon's formation, its evolution, and its ties to the Kuiper belt. Triton, after all, is not a typical moon. It is thought to be a captured dwarf planet, once roaming freely before Neptune's gravity claimed it. The chemistry preserved in its interior could tell us about the building blocks of the outer solar system, about how worlds like Pluto formed, and about the raw ingredients that may have seeded life on Earth. By probing Triton's depths, we would be peering into the history of our own cosmic neighborhood, into the icy archives of time itself. The evidence pointing toward Triton's ocean is compelling, but the certainty remains just out of reach. Voyager 2, for all its achievements, was only a flyby mission. It raced past Neptune and Triton in a matter of hours, its instruments not designed to probe deep beneath the surface. What it gave us was a glimpse, a whisper of the possibilities waiting below. To know for sure, humanity must return with new missions, orbital explorers, ice-penetrating radars, and perhaps even landers or cryobots that could drill into the ice and taste the waters below. Each of these possibilities represents not just a technical challenge, but also a philosophical leap. To send a machine to Triton's frozen plains is to declare that we are no longer content with gazing from afar, that we are ready to plunge into the unknown and ask the most daring of questions: are we alone? Even now, as we stand decades after Voyager's flyby, the dream of exploring Triton's ocean continues to inspire scientists. Mission proposals such as Triton imagine spacecraft swooping close to the Moon, mapping its surface in unprecedented detail, studying its thin atmosphere, and searching for signs of liquid beneath the crust. Though none of these missions have yet been launched, their very conception is a testament to the power of Triton's mystery. It continues to pull at our imagination like Neptune's gravity once pulled Triton from its wandering path. The ocean beneath its surface is not only a scientific puzzle, it is a symbol of possibility, a reminder that the universe keeps its most profound wonders hidden, waiting for us to muster the courage to look deeper. And what would it mean for humanity, standing here on Earth, to discover an ocean beneath Triton's crust? It would mean that oceans are not rare jewels but common features across the cosmos. It would mean that water, the elixir of life, flows in darkness across worlds we once dismissed as barren. It would mean that the story of life, whether it exists elsewhere or not, has more possible chapters than we could ever write on our own. Triton's ocean would remind us that the boundaries of the possible are not fixed. They are as fluid and dynamic as the hidden seas beneath icy moons. Even more profoundly, Triton's hidden ocean challenges us to reflect on our own planet. Earth's oceans cover more than 2/3 of its surface, yet even here, in our own backyard, we have only begun to understand their depths. The discovery of hydrothermal vents on the ocean floor decades ago showed us that life can thrive in conditions once thought impossible. Triton extends that lesson into the cosmos. It whispers that water does not need sunlight to sustain life, that life itself is not fragile but adaptable, able to flourish in the most unlikely places. To explore Triton's ocean would be to confront the possibility that Earth is not unique in its ability to nurture biology. It would be to face the humbling truth that we may live in a universe where oceans, and perhaps life, are the norm, not the exception. In the silence of space, Triton continues to orbit Neptune, a captured wanderer carrying within it the echoes of ancient tides. We cannot yet see beneath its icy crust, but the evidence grows, the clues accumulate, and the call becomes louder. There may be an ocean there, dark and secret, holding the potential to rewrite our understanding of the cosmos. Voyager 2 showed us the surface, strange plains, nitrogen geysers, icy volcanoes. The future beckons us to dive deeper, to break through the ice, to touch the waters below, and perhaps to encounter the most profound discovery of all, that we are not alone, that life is resilient enough to find a way even in the frozen shadows of Neptune's realm. Until that day comes, Triton's ocean will remain both a scientific puzzle and a symbol of hope, urging us to keep reaching, keep questioning, and keep exploring, for the greatest truths often lie hidden beneath the surface. When we speak of Triton, Neptune's largest moon, we are not simply talking about another icy body orbiting a distant planet. We are talking about a world that has the potential to reshape our understanding of planetary science and astrobiology. To explore Triton scientifically is to peer into the fundamental processes that built the solar system, sculpted its moons, and perhaps even allowed life to take hold in places once thought utterly barren. When Voyager 2 captured images of Triton in 1989, it was as though nature had opened a new textbook for humanity, one that rewrote what moons could be, and one that continues to pose questions far larger than we currently have the tools to answer. This moon is not just an object, it is a laboratory, a storybook, and a riddle wrapped in ice and orbiting at the farthest reaches of our planetary family. Its significance cannot be overstated, for within Triton lies the potential to bridge gaps in our knowledge of planetary formation, moon evolution, and the broader conditions necessary to sustain life beyond our own fragile Earth. For one, Triton's retrograde orbit alone makes it a point of fascination. Unlike most moons that circle their planets in the same direction as the planet rotates, Triton defies this rule. It moves against Neptune's spin, an unnatural dance that reveals it is no native child of Neptune. Rather, it was captured, likely stolen from the Kuiper Belt, a region of icy bodies beyond Neptune. This fact alone offers a treasure trove of insight. By studying Triton, scientists glimpse the chaotic ballet of gravitational forces in the early solar system, when giant planets were tugging, colliding, and reshaping their surroundings. To understand Triton is to better understand planetary migration. the way gas giants like Neptune shifted positions in the solar system's infancy, dragging smaller bodies with them or ejecting them into interstellar space. In this sense, Triton is a fossil, but not a fossil frozen in silence. It is a fossil still alive, active, and geologically dynamic, offering clues about what was and what still may be. Beyond its orbit, Triton's surface activity poses deeper questions. Voyager 2 revealed geysers shooting nitrogen gas into space, and these weren't just static relics of past activity. They were ongoing when the probe passed by. Such dynamism in such a distant, cold world tells us that heat exists beneath the icy shell. Where does that heat come from? It could be tidal heating generated by the gravitational tug-of war between Neptune and Triton. It could be radioactive decay within Triton's rocky core. Whatever the source, it forces scientists to rethink the boundaries of habitability. If an icy moon so far from the sun can sustain internal energy sufficient to drive geological activity, then the universe may be teeming with such worlds. And if many icy bodies across the cosmos hide such activity, then perhaps the conditions necessary for life are not the rare exceptions we once assumed, but rather a common thread woven into the fabric of planetary formation. The suspected subsurface ocean beneath Triton's crust intensifies its significance. On Earth, wherever there is liquid water, there is life. From hydrothermal vents deep beneath the sea to the icy caves of Antarctica, microorganisms thrive in the harshest of environments. Triton's possible ocean could be analogous to those environments, kept warm by internal heating and sealed beneath a protective crust. If even the simplest forms of life exist there, it would mean life is not bound to Earth's fragile conditions, but rather is a resilient force capable of taking root in the most extreme environments. For astrobiology, that would be a revolution. It would change the way we approach the question of life in the universe, shifting the narrative from "is life out there?" to "how many places like Triton could sustain it?" This reframes humanity's cosmic perspective. We are not a miracle in isolation, but perhaps a chapter in a vast and repeating story. The scientific significance of Triton also extends to its surface features, which are unlike anything seen elsewhere. Its cantaloupe-like terrain, rugged plains, and cryovolcanos reveal a history of constant renewal. Unlike the Moon or Mercury, which bear the scars of ancient impacts with little change since, Triton shows evidence of resurfacing. This means the Moon is young, not in age, but in appearance, its crust recycled by forces within. Studying this resurfacing process helps planetary scientists test theories about geologic activity on icy worlds. Do all captured bodies show similar features? Does tidal heating always result in cryovolcanism? Can these processes sustain an ocean long enough for life to evolve? Each question branches into countless others, reminding us how one icy moon can expand the boundaries of planetary science far beyond Neptune itself. Even its thin nitrogen atmosphere is a puzzle worth solving. At only 1/60,000th the density of Earth's atmosphere, it seems almost negligible, yet it reveals an active cycle of freezing and thawing, a system where seasonal changes drive the sublimation of nitrogen ice, which then falls back as frost. This thin veil of atmosphere is an analog for the atmospheres of other moons, dwarf planets, and even exoplanets beyond our solar system. By studying Triton's atmosphere, scientists can refine models used to understand Pluto, which shares similarities, or other icy worlds yet to be visited. It tells us that even the faintest, most fragile atmospheres hold clues to global processes and climate cycles on distant bodies. In this way, Triton is not isolated but interconnected with the study of countless other worlds. For planetary scientists, Triton represents both a puzzle and a promise. It is a puzzle because every fact about it defies expectation: its orbit, its surface, its geology, its atmosphere, and its potential ocean. It is a promise because in solving its mysteries, we may unlock deeper truths about how moons evolve, how planets shape their neighborhoods, and how life might take hold in conditions we once thought impossible. Every observation of Triton echoes outward, influencing not just the study of Neptune, but of icy bodies across the universe. By understanding one captured moon, we may begin to understand how many moons across countless star systems came to be. and how many might still be active, vibrant, and potentially habitable. The importance of Triton lies not just in what it is, but in what it represents. It bridges the gap between planets and moons, between geology and astrobiology, between the past and the future of the solar system. It is a testament to the idea that the solar system is not static, but alive with movement and change. When scientists look at Triton, they do not simply see a distant moon. They see a world with the power to answer questions humanity has carried since we first looked up at the stars. What makes a planet or moon alive? What conditions allow oceans to form beneath ice? How common might life be in the universe? Each of these questions, massive in scope, could be illuminated by the light of knowledge gained from Neptune's moon. In truth, Triton's significance is a reminder that exploration is not only about finding answers, but about daring to ask bigger questions. Every feature of Triton challenges assumptions, expands the boundaries of science, and demands that we refine our models of planetary evolution. It embodies the very spirit of discovery. As long as it remains unexplored by modern spacecraft, it sits like a locked vault at the edge of our solar system, holding secrets that could redefine how we see the universe and our place in it. And that is the essence of its scientific importance. It is both known enough to intrigue us and unknown enough to transform us. In the end, Triton stands as one of the greatest natural laboratories in the solar system, a celestial canvas on which the forces of formation, evolution, and possibility are painted vividly. By studying it, we do not merely learn about one moon, we learn about worlds beyond, about ourselves, and about the universe that cradles us all. That is the true significance of Triton, a frozen giant whispering truths about life, time, and creation, waiting for us to listen. When humanity gazes into the depths of space, the distant light of Neptune and its moon Triton remind us not only of science and discovery, but of something far more intimate, the essence of our own human spirit. For Triton is not simply an object of scientific curiosity, it is a mirror reflecting our deepest impulses, resilience, imagination, and the unyielding desire to push beyond the horizon of the known. The inspiration that Neptune's moon gives us cannot be measured in data or equations alone. It must be felt in the heart, for it embodies the story of humankind's relentless pursuit of meaning in a universe that often seems cold, vast, and indifferent. To look upon Triton is to be reminded that even in the most inhospitable places, there is activity, renewal, and the possibility of life, parallels that speak directly to the resilience of our own existence. Consider the cold truth of Triton's environment, a world cloaked in nitrogen frost, bathed in perpetual darkness at the farthest reaches of our solar system, where temperatures plunge to nearly absolute zero. By all accounts, it should be dead, still, and silent, and yet, against all odds, it shows us geysers that erupt with icy plumes, terrains that are reshaped, and hints of oceans hidden beneath its crust. Triton stands as a symbol that life, whether biological or geological, finds a way to persist, to adapt, to resist stillness even when surrounded by impossible odds. In this, we find not just scientific marvel but human inspiration, for does this not echo our own story as a species? Humanity, too, has thrived where the odds seemed impossible. Through ice ages, wars, famines, and the challenges of survival, Triton is a frozen moon, but its vitality is a cosmic metaphor for our own resilience. This inspiration is amplified by the sheer distance of Triton from us. At over 3 billion kilometers away, it lies in a region of space so remote that only one spacecraft, Voyager 2, has ever seen it up close. For generations, it has lingered in the background of astronomy, waiting quietly for human eyes to notice, and yet, when those images finally came in 1989, the moon was anything but ordinary. Its strangeness, the retrograde orbit, the active geysers, the smooth, young surface, spoke volumes. It told us that even in the most distant corners of the universe, where human imagination rarely dared to wander, there exists beauty and mystery beyond measure. That realization inspires us to dream bigger, to see the universe not as a cold void but as an infinite frontier where wonder waits around every corner. Triton also reminds us of the courage of exploration. When Voyager 2 flew past Neptune, it carried with it decades of human effort, ambition, and courage. That mission was more than a spacecraft crossing space. it was humanity itself extending its reach. For the people who worked on Voyager, Triton's images were proof that all those years of effort were not in vain. They were a message to the entire world that when humanity works together, we can send our touch to the edges of the solar system, unveiling mysteries we once thought unreachable. That same spirit of daring is alive in every child who looks up at the stars and dreams of what lies beyond, in every scientist who spends sleepless nights analyzing data, and in every explorer throughout history who left the safety of home to pursue the unknown. Triton is a continuation of that eternal story, the story of courage in the face of distance, risk, and uncertainty. On a deeper emotional level, Triton inspires because it speaks to the human yearning for connection. We often feel small in the face of the universe's vastness, wondering whether we matter in the grand scheme of things. Triton whispers back to us, yes, you do. For this moon, distant and strange, becomes meaningful precisely because we are here to see it, to wonder about it, to study it. In exploring Triton, humanity is not just learning about a frozen world. We are making it part of our shared story. The very act of assigning it meaning shows the power of human consciousness. The universe may not need us to exist, but in observing and exploring it, we give it narrative, purpose, and significance. Triton inspires us because it becomes a canvas for our need to belong to something greater than ourselves. Even the possibility of hidden oceans beneath Triton's crust strikes at the core of human imagination. What if there is life beneath that frozen shell? What if the story of life is not confined to Earth but is scattered across the cosmos, waiting to be discovered? These questions are not just scientific, they are existential. They ignite our imagination in ways no frontier on Earth ever could. They push poets to write, philosophers to ponder, and scientists to dedicate their lives to exploration. Triton, in its silence, asks us the most profound of questions: are we alone? And even if the answer is yes, the pursuit of that answer drives us to dream, to reach beyond ourselves, to become more than we were yesterday. The symbolic value of Triton goes further still. It represents the defiance of expectations. Scientists expected a dead world, but found activity. Humanity often expects limitations, but through resilience we overcome them. Triton stands as a symbol that the universe is always ready to surprise us if only we dare to look deeper. It teaches us humility, reminding us that we do not yet know the full story of our own solar system, much less the cosmos. Yet at the same time, it fuels confidence, for it shows that even with limited tools, humanity has already uncovered so much. Imagine what more awaits when we return to Triton with modern spacecraft, equipped with instruments capable of drilling into its icy shell or mapping its subsurface oceans. The thought alone inspires generations to dream of becoming engineers, scientists, and explorers who will one day bring those discoveries to light. For future generations, Triton holds the power of motivation. It stands at the edge of what we have achieved, daring us to push further. Just as the moon inspired the Apollo missions, just as Mars inspires current generations, Triton could inspire the future explorers who will extend human presence farther than we now think possible. To know that there is an ocean beneath the ice of a distant moon may one day drive humanity to send missions there, to dive beneath its crust, to see firsthand what secrets it hides. The thought of being the first to witness such a discovery fuels ambition, perseverance, and creativity. And these qualities are not just needed in space exploration, they are qualities that elevate every human endeavor, from art and literature to science and leadership. The story of Triton also ties us to our ancestors. For centuries, humanity has looked to the sky for guidance, meaning, and inspiration. Ancient civilizations mapped the stars, created myths, and aligned temples with celestial events. Triton, though unknown to them, is part of that same sky. Today, as we study it, we continue the work they began. In doing so, we honor the timeless human desire to reach upward, to look beyond the immediate horizon, to believe that there is more. This continuity is inspirational because it shows that exploration is not just a modern pursuit. It is written into the very fabric of who we are as human beings. Perhaps most of all, Triton inspires because it embodies hope. Hope that even in the darkest corners of the universe there is activity. Hope that we are not alone. Hope that the universe is not a barren emptiness but a vibrant, dynamic place filled with surprises. In times when humanity faces challenges, wars, climate change, inequality, it is easy to feel small and powerless, yet Triton stands as a reminder that we are capable of extraordinary things. If we can send a machine billions of kilometers away to glimpse the secrets of a distant moon, then surely we can solve the problems here on Earth. The same creativity and determination that drives us to explore space can also drive us to build a better future for ourselves. In this way, Triton is not just a moon, it is a beacon, and so Neptune's moon, silent and distant, continues to speak to us in ways words can scarcely capture. It tells us to be resilient, to be curious, to be daring. It tells us that even in the coldest, darkest corners, there is movement, there is possibility, there is life in some form. It inspires us to keep asking questions, to keep pushing boundaries, and to keep believing that our story as a species is not yet finished. For Triton, like all great symbols, reminds us not only of what is, but of what could be. When we talk about Triton and its importance to humanity, the conversation inevitably leads us to the question of what comes next. It is not enough to simply marvel at the date Voyager 2 sent back in 1989, as groundbreaking as those images and findings were. Humanity's true strength lies not only in discovery but in the courage to return, to build upon what we have learned, and to seek answers to the questions that remain. And no question looms larger than what future exploration of Neptune's moon might reveal. Triton is a world that practically demands a return, for it holds mysteries that could reshape science, astrobiology, and our place in the cosmos. The future exploration goals surrounding Triton are vast and ambitious, but they are also deeply necessary, for they represent humanity's next great step outward into the universe. The first goal of future exploration is to simply return and observe Triton with modern instruments. Voyager 2, though revolutionary for its time, carried technology from the 1970s. Its cameras, sensors, and instruments, while remarkable in what they achieved, are primitive by today's standards. The world it revealed, a moon with geysers, young surfaces, strange terrain, and perhaps oceans beneath the ice, was shown to us in tantalizing glimpses. But glimpses are not enough. We need orbiters equipped with higher resolution cameras, spectrometers, and radar systems capable of penetrating the icy crust to detect subsurface oceans. Just as the Galileo mission transformed our understanding of Jupiter's moons, and the Cassini mission revolutionized our view of Saturn's system, a dedicated Neptune orbiter could revolutionize our understanding of Triton. It could map its surface in exquisite detail, track the activity of its geysers, and confirm whether liquid water lies beneath its crust. Another major exploration goal is to study Triton's atmosphere. Thin and tenuous though it may be, its nitrogen atmosphere is dynamic and seasonal, freezing and sublimating in response to Triton's orbit around Neptune and the Sun. By returning with instruments designed to study atmospheres, we could better understand not only Triton's thin veil of gases, but also how atmospheres evolve on small, icy worlds. Such studies could inform our understanding of Pluto, Eris, and other Neptunian objects, as well as exoplanets far beyond our solar system. Triton, therefore, is not just a world to be studied for its own sake. It is a key to unlocking patterns and processes across countless celestial bodies. Perhaps the most exciting and ambitious goal of all is to probe beneath Triton's icy surface in search of a subsurface ocean. If Triton does indeed harbor such an ocean, it becomes one of the most promising places in the solar system to search for extraterrestrial life. Missions could be designed to use radar to confirm the depth and extent of these oceans, much like the instruments used to probe Europa and Enceladus. In time, landers or even cryobots, machines designed to melt through ice, could be deployed to directly sample the waters beneath. Imagine for a moment the magnitude of such a discovery, a probe landing on Triton, drilling into the ice and transmitting data about what lies beneath. If we found even microbial life, it would mean life is not a rarity, not a miracle isolated to Earth, but a cosmic inevitability. Such a discovery would alter not only science, but philosophy, religion, and humanity's entire perception of its place in the universe. Another crucial exploration goal is to understand Triton's origin and capture. Its retrograde orbit tells us it did not form alongside Neptune, but was instead captured from the Kuiper belt. But how exactly did this happen? What was Triton before it became Neptune's moon? Was it once a dwarf planet like Pluto, complete with its own atmosphere, mountains, and seas? If we study its composition in detail, comparing it with Pluto and other Kuiper belt objects, we could reconstruct its history. Doing so would not only illuminate Triton's past, but also the broader story of how giant planets shaped the solar system in its early days. Missions to Triton would therefore not just be about one moon. They would be about retracing the chaotic dance of worlds that gave birth to the solar system we know today. Future exploration also holds the promise of understanding Triton's geologic activity. Those geysers seen by Voyager 2 were not random. They suggest ongoing internal processes, heat sources, and perhaps even tidal interactions with Neptune. By monitoring these geysers with orbiters and landers, scientists could uncover the mechanisms behind them. Are they driven by seasonal sunlight heating the surface, or do they originate from deeper internal activity, hinting at a more complex and dynamic interior? The answers to these questions would not only redefine Triton, but would also expand our models of how icy moons throughout the solar system behave. There is also an inspirational and symbolic goal in returning to Triton. Humanity has long been driven by frontiers, by the oceans we sailed across, the mountains we climbed, the poles we reached, and eventually the skies we conquered. Space is our newest and most profound frontier. By setting our sights on Triton, one of the most distant and mysterious moons, we are sending a message to ourselves and to future generations that no distance is too great, no challenge too daunting, no mystery too deep. The very act of planning a mission to Triton would inspire generations of scientists, engineers, and dreamers, just as Apollo once did with the moon and Perseverance is doing with Mars. To achieve these goals, international collaboration may be essential. A mission to Neptune and Triton would be long and costly, taking more than a decade to reach its destination. But such a mission would unite nations under a common banner of exploration, proving that when humanity works together, our reach extends beyond Earth's boundaries. Just as the International Space Station became a symbol of global cooperation, a mission to Triton could be the ultimate symbol of humanity's shared desire to explore the unknown. Technological innovation will also be a central part of this endeavor. New propulsion systems such as advanced ion drives or even nuclear-powered propulsion may be required to cut down travel times to the outer solar system. Power sources capable of sustaining spacecraft in the dim sunlight of Neptune must be perfected, such as advanced radioisotope thermoelectric generators. The technological challenges are immense, but every challenge overcome will not only bring us closer to Triton, but also provide technologies that benefit life here on Earth. In this way, the exploration of Triton is not just about space, it is about progress for humanity itself. Another long-term exploration goal may be to establish a broader presence in the outer solar system. Missions to Neptune and Triton could pave the way for humanity to eventually station orbiters, telescopes, and robotic outposts in that distant region. From there, the Kuiper belt would be within easier reach, and even interstellar probes could be launched. Triton could thus become a gateway, a staging ground for humanity's expansion into the galaxy. The thought of such a future transforms Triton from a distant moon into a symbol of human destiny. And finally, the exploration of Triton carries with it the goal of perspective. Every time humanity ventures farther into the cosmos, we return not only with data, but with a new way of seeing ourselves. When Apollo astronauts looked back at Earth from the moon, they gave us the Earthrise image that forever changed how we think of our planet, small, fragile, and alone in the vastness of space. When Voyager 1 turned its camera back toward Earth, it gave us the pale blue dot that reminded us of our shared humanity. When we return to Triton, we will gain another perspective, one that tells us that even the coldest, most distant places are worthy of exploration, that no frontier is beyond our grasp, and that humanity's spirit of curiosity is boundless. In the end, the future exploration goals of Triton are about more than science. They are about daring, inspiration, and the relentless human spirit. They are about sending our presence to the edge of the solar system, about seeking answers to questions that have haunted us for millennia, and about proving to ourselves that we are capable of greatness. Triton is not simply a moon, it is an invitation to return, to discover, to be humbled, and to be inspired. It asks us to risk, to dream, and to believe that within its icy crust lie answers that could change everything we know. And perhaps when we finally set our instruments upon its surface and gaze into its hidden depths, we will not only discover the secrets of Neptune's moon, but also rediscover the best within ourselves.